Good afternoon, students. So, in this lecture, we will continue with the operators in quantum mechanics. Now, in the last lecture, I told you that all dynamical variables in quantum mechanics are represented as operators. And we have seen that these operators are linear and Hermitian in nature. And we have talked about what are linear operators and what are Hermitian operators. And I gave you a list of operators in quantum mechanics which you should be knowing, like the position operator, the momentum operator, the kinetic energy, potential energy operator, the Hamiltonian operator. Now today I will discuss with you another important operator, that is the angular momentum operator. So angular momentum is a dynamical variable that we are speaking of here. So the angular momentum we know by definition is r cross p, where r is the position coordinate and p is the linear momentum. So if you have to represent this in quantum mechanics, now you will write L cap is equal to r cap cross p cap. So we know r cap vector is represented as r and p cap we know is represented as minus I h cut, the del vector, where I is the imaginary number and h cut is h by 2 pi. So it is minus I h cut r cross del. So now this is how we represent the angular momentum operator in quantum mechanics. Now we should write down the x component of the angular momentum operator from here. If you write down the x component, it will be a y cap pz cap minus z cap py cap. So pz cap is the z component of the linear momentum. So when you're writing the x component, you start with y followed by pz cap, and in this term the z and y gets interchanged. Next, Ly cap. Ly cap you are writing, so we will start with the z. So z cap, px cap, and here we will again interchange minus x cap, pz cap. And next is the z component. So x cap, py cap, minus y cap, px cap. Now all these you can get from here. But to apply in different problems, you need to know these expressions. So the rule to know it is that it follows the cyclic order of this x, y, z. When I am writing the x component, I start with y followed by z, and in the second term I interchange y and z. When I start with the y component, I start with z followed by x, and in this second term again x and z gets interchanged. And when you are starting with z, you have to again go back to x, start with x followed by y, and in this second term this y and x will get interchanged. So these are the angular momentum operators in quantum mechanics. Now I will be giving you problems in your online test as well as in your Google Classroom assignment regarding these different operators, where you have to apply the knowledge of these operators and solve the problems. Now I will discuss another topic that is related to operators also, that is the commutators. Okay, so we will talk about what are commutators, and we will talk about the commutation relation of operators, different operators. So let us talk about commutators. What is meant by that? So if you have an operator A cap and you have another operator B cap, then these two operators, they are said to commute with each other if A cap B cap is equal to B cap A cap. So that is A cap B cap minus B cap A cap is 0, and this we write within third bracket as A cap comma B cap. So this third bracket A cap comma B cap means A cap B cap minus B cap A cap. So if this relation is satisfied, then I will say that these two operators, they commute with each other. But if it does not satisfy, that means I get a result which is not equal to 0, then they do not commute with each other. Okay. Now what is the significance of this? So if this condition is followed, that means A cap B cap operating on a function psi will give me the same result as B cap A cap operating on the function psi. That means B cap first operating on psi and then A cap operating on it is the same as A cap operating on psi and then B cap operating on it. So this means that it doesn't matter whether I measure B cap first or A cap first, or whether I measure A cap first and B cap then. So that means that these two operators can be measured simultaneously. So these two operators definitely will represent some dynamical variables. That means the dynamical variables that these two operators are measuring, they can be measured simultaneously. And if it is not satisfied, that means if this is giving a result not equal to this, that means these two operators cannot be measured simultaneously. So let us just work out one example of the commutation relation. So let us talk about two operators x cap and px cap. Okay, and let us see that what is the commutation relation between them. So what we will do, we want to find out this, what result this gives. So let us see what result this gives. So it will be, as per the definition, it will be x cap px cap psi minus px cap x cap psi. Now I will write down the meaning of these operators. So it is x variable, px cap is minus I h cut del x over psi minus again px cap is minus I h cut del x and x cap is x over psi. So now I will just do the simple differentiation. So minus I h cut x del x operating on psi is del psi del x, and this is the constant, so I can just bring it out. Here it is plus I h cut. Now here del x operates on x and psi. So mind it, here psi is also a function of x here. So then what I get, minus I h cut x del psi del x plus I h cut del x operating on x psi will give I h cut psi plus I h cut x del psi del x. So these two will cancel, as you can see, and what is the result that we have got? I h cut psi. So that means the result is x cap px cap. This gives me the result as I h cut. So it does not give me a zero answer. It gives me I h cut, which shows that these two variables, they do not commute with each other, and that is why you know from the Heisenberg's uncertainty principle that you cannot measure simultaneously the position and the momentum in quantum mechanics, which you see here that the position and operator and the momentum operator, they do not commute with each other, so they cannot be measured simultaneously. Okay, so this is just one example I give you. Now in your assignments, I will be giving you other commutation relations which you have to work with other operators. Next, so this was operator on the postulate 2 of quantum mechanics that we have discussed so long. So now we will go to postulate 3. So postulate 2 was that all dynamical variables are represented by linear and Hermitian operators. Now let us see what postulate 3 says in quantum mechanics. Though I have mentioned this a little bit while I was doing the operators, that postulate 3 says that the results of the measurements of all dynamical variables, they are eigenvalues of any operator a cap which satisfies the eigenvalue equation a cap psi equal to, say, lambda psi. So if here lambda is the eigenvalue which we have talked about already. Lambda is the eigenvalue. This is the result of this operator a cap which we are measuring, and a cap represents a dynamical variable. So lambda is the eigenvalue, psi here is the eigenfunction, and a cap is the operator corresponding to this. This is called the eigenvalue equation in quantum mechanics. So given a psi and a cap, you should be able to find out the possible values of that operator. That means you should be able to find out lambda. Or sometimes we get problems like this, that whether a function given to us, whether it is an eigenfunction or not. For example, if we take the function psi equal to sine x, okay, and the operator a cap is del 2 del x square. Now I just tell you to check whether this sine x is an eigenfunction. Now because I told you that if a cap operating on psi x gives you lambda into some different function, say phi x, then definitely it is not an eigenvalue equation, and psi x is not an eigenfunction. Okay, so here the function is sin x. Okay, so now let us operate it. So a cap psi, what I will get, del 2 del x square operating on sin x. So it is del x of del x operating on sin is, because del x square means del x of into del x. So this will give you del x of sin x is what? Cos x. And del x of cos x will give you minus sin x. So a cap operating on sin x gives you minus, here minus into nothing here means actually it is 1, minus 1 into the sin x back. So here I say that sin x is the eigenfunction and the eigenvalue here lambda is given as minus 1. Okay. Now this is one example where sin x is an eigenfunction. Now I give you another example. Say the function instead of being sin x is sin square x and the operator remains del 2 del x square. Then let us see whether this sin square x is an eigenfunction or not. So this is sin square x, sin square x. So sin square x, if you differentiate, what you will get? This will give you del x into 2 sin x cos x. So you also just do it with me. If you differentiate, what you get? It will be 2 cos square x minus 2 sin square x. So it will be 2 cos square x minus sin square x. So definitely I am not getting back the same function sin square x. Instead I am getting a new function cos square x minus sin square x multiplied by this. So I will say that this sin square x is not an eigenfunction. Okay. So this is the example of a function being eigenfunction or not. And as I said that if I provide you with psi and a cap, you can also find out the eigenvalue which I have shown in the previous case. Now the last postulate, the fourth postulate, the last postulate I will be discussing in the next class, and in fact we will be then applying that straight away the Schrodinger's equation. We will start from the next class. So I will just talk about the fourth postulate here. Though the application of that fourth postulate, we will be doing it when we apply Schrodinger's equation. So postulate 4 says that the expectation value or the average value of a large number of measurements of dynamical variables for a normalized state, it is given by, so if I say that a cap is my dynamical variable, so if I want to find out the expectation value of a cap, it will be given by psi star a cap psi dx. So the expectation value of this a cap, the dynamical variable, is given by this for a normalized state. Now if the state is not normalized, then what we have? Then the expectation value will be given by psi star a cap psi dx divided by psi star psi integral psi dx. Because for a normalized case, you know that this is equal to 1. So if it is not normalized, then you have to divide it by this denominator. So I am just writing it once more. Let me just write it because the ink has turned low for that. So it is this divided by integral psi star psi dx. If it is not normalized. If it is normalized, then this. So this is the average value of the large number of measurements of the dynamical variable. So this is what is postulate 4. So with this we will end